Hi, everyone. My name is Caitlin. Thank you for being here. Uh-oh. Oh, my laptop went asleep. Okay. Okay, great. Today I'm talking about virtual machines and containers and how micro virtual machines are sort of the best of both worlds. Okay, so a little bit about me. Oh, and why am I speaking about this? So my name is Caitlin Sang. I started off my career at the Johns Hopkins Applied Physics Lab, working in a research group that did defensive cybersecurity research, and specifically I focused on cloud security. I worked there for a bit, and then I went to go to a startup in the Maple Lawn area called Unveil, and we worked on private information retrieval. And now I'm currently working at a small startup called Ginger Cybersecurity, and we are creating a secure, minimal operating system to run on MicroVMs. And as part of my work at my current role, I'm trying to stay very current on the landscape of virtualization and containerization, and so I wanted to share that all with you today. So I just wanted to do a quick show of hands. How many of you are already familiar with the concept of a microVM? Okay, so some people. And is anybody already using microVMs in your workflow or in your day-to-day work? Okay, all right, sounds good. So let's talk about it today. So I'm gonna start by talking about a brief history of virtualization and containerization, and I'm gonna focus on some of the threat vectors of what we're concerned about or what we're trying to address, and then I'm gonna talk about some of the benefits of microVMs. Okay, so now we're going way back to the 1960s and 1970s when the main computing technology was a mainframe. So there were these big, large, expensive mainframes, and the goal with that was to make it more efficient for people to timeshare. And so that was when the first concept of virtual machines came about. At the time, it wasn't called virtual machines necessarily. It was a program called CP in CMS. The CP stood for Control Program, which was essentially the very first hypervisor. CMS it changed names a couple times, the Cambridge Console or Conversational Monitor System. And so the Control Program acted as what we now call a hypervisor. Fun fact, the name hypervisor came because what they considered a supervisor was the guest operating system kernel. That was the supervisor, and they needed something to supervise those supervisors. And so that's how the term hypervisor was for something that's supervising the supervisors. Okay, and so we called this a type 1 hypervisor. This is where you have the control program or the hypervisor directly installed on the hardware. And as a side note, around the same time, we also saw some container-like primitives being integrated into the Unix kernel. Chroot or change root was a utility that would allow the apparent file system to be changed for a running process. Developers who were working on the Unix kernel at the time used it to sort of develop and iterate on the kernel without messing up their operating system that they were operating on. Okay, so for a bit there was some slow and steady progress, but things really took off in the 1990s and the 2000s. At this time, personal workstations were a little more common at this point, and developers wanted a way to change operating systems without powering down their system. And so we came up with type 2 hypervisors, where maybe you already have a host operating system running on your system and you want to install a hypervisor on there as well to run your virtual machines without powering down your main desktop. And so here we saw innovations such as VMware introducing VMware Workstation, which was a proprietary solution. Shortly after, VirtualBox which was released, which was an open source solution. The QEMU team made the first stable release. In addition, we also saw Intel and AMD integrating hardware virtualization support to make virtualization faster on your desktop. Okay, and then now we're talking back again about type 1 hypervisors. The industry was standardizing on x86 hardware, moving away from proprietary RISC-based architecture. VMware took some of the innovations that they made for the Type 2 hypervisors and introduced them in their Type 1 hypervisor, ESX, which could run bare metal. We saw Zen 1.0 was released, and KVM was merged into mainline kernel, which allowed some of the virtualization support from directly within the kernel. Okay, and then we saw another leap in innovation with containers in the 2000s, 2010s time period. The goal here was to sort of isolate processes and have reproducible environments for development and deployment. You could sort of create your container locally and then deploy the exact same thing on the cloud. So what sort of enabled this leap in innovation was namespaces and C groups were merged into the Linux kernel. This allowed you to group together processes that were running logically, and then namespaces allowed you to isolate what those processes saw in the context of the wider system. The very first iteration of a container, sort of tying all those technologies together, was Linux containers, LXC, but they were a little bit bulky to use and they didn't fully take off. However, in 2013, Docker was released, which sort of simplified the container experience. They introduced things like an image registry where you could easily download the images. They had a very simple command line tool for running containers. You could just say Docker up or Docker run. And then shortly after, only a year after Docker was released, Kubernetes was released, and that gave you the orchestration piece where you could sort of control all your containers all at once and manage them that way. And I love this graph here. Let's see. So this is a graph of Google search trends over time. And I know it's not an exact replica of how many downloads were happening at that time, but it just shows developer interest. So the blue line is searching for VMware, the red line is searching for VirtualBox, and the yellow line that really takes off there is searches for Docker, and the green line after that is containers. And this was a really wild time for me. At the time, I was on a team that was contributing to OpenStack, which is primarily built on the infrastructure for running virtual machines as a cloud service. And right around the time Docker and Kubernetes were being released and growing in popularity, we would go to these OpenStack summits and people were talking about, oh, Kubernetes is the next big thing. So I really feel like I lived this whole sort of transition here. So why did they take off so quickly? My take is that we had already built up this infrastructure around VMs and orchestrating them. And then containers came along and showed that you could do it so much more quickly. You could download things quickly, launch them quickly. The containerized applications were quicker to start than booting a virtual machine, and you could pack so many containers all in the hardware all at one time. But what about security? Are there any security implications here? Well, actually, yes. Part of the reason why containers are so popular, such as their speed and their small image format, have sort of a little bit of security risks involved in them, and I'll go more into the architecture of why that is. So here we're going to talk a little bit about container escape, which is one of the main reasons why people talk about why containers are less secure than virtual machines. So here we have some containers running on their container runtime, such as Docker. We have the host operating system, and then we have all that running on some hardware. Now, the thing about containers, about why they are able to boot so quickly, is because they are sharing the host kernel. So in that container image, it's not a full operating system. They're sharing, all the containers are making syscalls and interacting with the host kernel directly, which is why the images can be so small. It's because they don't contain the whole operating system. Why they can start up so quickly is because you don't have to wait for the whole OS to boot. It's just like your one simple process. And we'll go from there. So here we're going to focus on App A. Say we're responsible for keeping App A secure. And say, for example, a different app running on our same host, App B, is subject to a cyber attack. That's bad news for them. But what does that mean for us? Over here in App A. And so we're going to look at some CVE numbers real quick. Because all of those containers are sharing the host kernel system, we're looking at the CVEs for the kernel now. in 2025, for example, we saw between like 5,000 and 6,000 kernel CVEs reported. There's sort of a rough estimate that maybe 30 to 40% were either high or critical severity. And it seemed like there were reports that 7 were seen exploited in the wild. So not only are we concerned about that container, the kernel that everyone is sharing, but we're also concerned about the container runtime. And so we saw around like 5 or more container runtime CVEs reported explicitly. So now not every single CVE means that there's a container escape. I'm just trying to illustrate that there's sort of a large attack surface there, and there's more opportunity, more potential there for something to happen. And so once an attacker escapes that one container, all of the rest of the containers are at risk. So how about a VM escape? Can the same thing happen there? So let's say, again, we are responsible for app A, we're concerned about app A, but a different app running on your host is, in a different VM is compromised. So yes, I will admit that VM escapes do happen. In 2025, we did see a critical trio of CVEs that could be chained together affecting VMware, but that in general, that hypervisor space is much, the attack surface is much smaller. There's much less code going onto the hypervisor that makes up the hypervisor as compared to the whole Linux kernel. And then also, if there's an attacker trying to escape out of the VM, they have to escape all of that hardware virtualization emulation to get out of the virtual machine. And so that was, talking about container escape, virtual machine escape. Here are some other threat vectors we may want to consider. There can be image or supply chain attacks, like if your container image or your VM image that you're downloading is at risk. Orchestrator attacks, if you're using extra software to manage all of your containers, that is also a whole nother attack surface. Side channel attacks, where maybe the attacker is not accessing your system directly, but they can sort of predict the memory that's going to happen in your virtual machine and exploit your isolated virtual machine in that way. Also, additionally, there can be application layer attacks, either in code that you've written yourself or in libraries that you're pulling in. Like we see that sort of thing happen with log4shell, where everyone was using log4j, and attackers were able to access the shell through that threat vector. So given all these threat vectors, we've seen the growth of virtual machines and containers. What is sort of the next trend? The trend that I'm seeing is generally these technologies are focusing on reducing that attack surface. And there's different companies out there trying to solve these problems for containers. We're seeing companies trying to provide base container images that have been audited for CVEs beforehand, distruless container images that only run exactly your application and its dependencies and not much else. We see solutions that are trying to intercept syscalls to the kernel. And additionally, we see solutions where you're trying to wrap that container in a VM and just sort of launching it that way. But let's go back to our virtual machine use case. The Linux kernel has been around for a long time. Hardware has advanced significantly since Linux was first around. So maybe even if virtual machines were slower to start, maybe we can strip out a lot of that functionality and make our virtual machines much smaller and make them just as lightweight and as speedy as a container. Additionally, I don't mean to make this an AI talk, but it feels a little bit like the elephant in the room. I'm seeing people want to sandbox their AI agents on their desktops as their AI agents are pulling in all of these random dependencies, and we want to try to control that and make sure that they aren't pulling anything too risky. I also see a need where AI attackers are automating their attacks with AI, and that speed of CV announcement to attacks in the wild is becoming shorter and shorter. And so as defenders, we need to sort of reduce our attack space as much as possible. So thinking again about these virtual machines, in the previous slide I mentioned a few different solutions for containers, but layering containers with virtual machines, let's think about deploying our applications directly on very lightweight, very small MicroVMs instead of layering our containers around with virtual machines. So, adding a new era to my timeline of virtualization and containerization, MicroVMs. So I am not the person who coined the term MicroVMs. I believe AWS has that honor. They released Firecracker in this time period. They had a use case where they wanted to run user-submitted code in their Lambda jobs, and containers didn't provide the amount of isolation that they needed, so they turned to MicroVMs to run user-submitted Lambda jobs. And they've open sourced this since then. So because, here, I'll go on to my next slide. So what exactly is a MicroVM? Well, there's not exactly one specific definition. In general, it's a lightweight virtual machine. So I spent so much time talking about the architecture of VMs and containers. It's the same architecture, just stripped down, a lot smaller. Virtual machines, MicroVMs are purpose-built for a specific task. That's how we can take the traditional virtual machine architecture and make it just as lightweight as a container by stripping down everything that we don't need. So we can achieve this. We can generally achieve some combination of faster boot times, smaller images, stripped down kernel. We can even drastically reduce the number of files in your default file system, emulate only the necessary devices. You can have a fewer number of processes running on your system. So we talked earlier about type 1 and type 2 hypervisors. MicroVMs can run in either situation, but because of their stripped down and purpose-built nature, you're probably going to do either one or the other. So your sandbox that you're going to run your AI in may not be the same MicroVM that you're deploying your server applications to the cloud in. Okay, so let's see. How does this impact our security of our virtual machines? So MicroVMs have the same security properties of general purpose VMs that we were talking about before as far as the isolation goes, plus more. Because if we've stripped down the hypervisor to remove all the unnecessary functionality, there are fewer lines of code, which would lead to hopefully fewer CVEs. If you've stripped down the kernel and removed all of the legacy devices and the legacy drivers that you don't actually need for your purpose, that kernel can boot a lot faster. If you have a smaller number of files in your file system because you're only running exactly the app that you want to run, you can measure and audit your system a little bit more accurately. You can attest that only certain things are running on your system at a given time. So in summary, I don't mean to hate on containers. There's a time and place for every technology, I really feel. If you really trust your code and you really trust your architecture, maybe containers are still the right solution for you. You can still run containers very densely. MicroVMs, however, if you have any other sort of security concerns, such as the isolation, and needing to remove any sort of the extra functionality, MicroVMs will improve on that boundary compared to containers, and they may still operate just as speedily and lightweight in the same sort of realm as containers because of that guest kernel isolation. Okay, so that concludes my talk. I'm out at a booth for Ginger Cybersecurity, my company, out in the lobby, if you want to talk about our operating system and how we're using MicroVMs. And so I guess now at this time I can take some questions. Okay, yes?
Being familiar with VMs and building containers, I've never built a MicroVM, but how would I get started figuring out how to build a MicroVM for a simple Python app?
Yes, a very good question. So the question was how to get started building MicroVMs for like a simple Python app, for example. There's a few different technologies now. It sort of depends on your purpose. Like if you're deploying this app in the cloud, I'm a little bit partial to our own operating system that has its own tool chain, but there's also Firecracker. Firecracker has really great documentation. I believe Firecracker claims that it can generally run any Linux-based operating system, but they do offer their own operating system image that is very pared down as well to help solve that space. Yeah, that is the tool, and it's open source, and or yes, so okay. Okay. Oh, yes. Oh, okay. So the question was, have we done any testing on host-based security systems such as EDR? Is that correct? Yes. The short answer is I personally have not done that. That would be an interesting experiment. At least for how we're deploying them at St. Ginger Cybersecurity, we have made a bet on sort of our own lockdown system of making our system immutable and making the files read-only where they need to be. But that would be interesting to try to run an experiment such as that, I think. So, okay. Okay, well, I don't see any more questions, so thank you so much.